Hi everyone, welcome to section 9.3 where we're actually going to be using your grapher to analyze relations or functions. So when we talk about analyzing graphs, we've got a whole bunch of criteria we need you to follow or look for. First and foremost, we have what we already know is the domain and the range. So remember, domain is how far left to how far right the graph goes. Your range is bottom to top. So how low does that graph go to how high that graph goes. The next point of analysis we want you to find are the x and the y intercepts. And again, we're going to be doing all of these functions using your calculator. So we'll be showing you or reviewing some of those calculator skills. So we want to know where your graph crosses both the x-axis or the y-axis. Now, the next point of analysis talks about what we call positive or negative intervals. So positive or negative intervals, to be very clear, have specific parts of the graph that we're looking for you to explore. So if we want to know where the graph is positive, we want to know which parts of the graph are sitting above the x-axis. So any branches of the graph or any portions of the graph that are sitting above the x-axis are going to be considered positive, while negative parts of the graph are going to be the parts of the graph that are sitting below the x-axis. So if I were to draw a quick little function, let's say even a parabola that looks something like this, let's say, I'm going to highlight the parts of the graph that are positive, but I want to give you some points to deal with. So let's say this x-intercept has the value of negative 3, 0, hypothetically speaking, and this intercept has an x-intercept value of 3, 0. So we know where the graph crosses that x-axis. Positive parts of the graph are going to be the purple parts that are sitting above that axis. So if you can imagine that everything below the axis doesn't count, but everything above the axis constitutes the positive parts of the graph, we need to be careful about how we are writing our interval for graph parts that are positive. So in this particular case, the graph part is positive from left to right. So positive or negative parts of the graph are always with reference to x. So we would say it's positive from negative infinity, and not because that tail's up high, but because that tail sneaks as far to the left as you can imagine. So the graph is positive from negative infinity to negative 3. And we have to use a round bracket at negative 3 because at negative 3, I'm not sitting completely above the x-axis, I'm on the x-axis, or I'm in transition. So this graph is positive from negative infinity to negative 3, and then I'm going to put a little union, which means together with. There's another part of the graph that's positive. The second part of the graph starts when x equals 3 and continues to the right forever. So the further I trace to the right, the more above the x-axis I actually become. So we say that the graph is positive from 3 to infinity as well. So once again, when we're talking about positive or negative parts of the graph, you want to be talking in terms of x values. From x is negative infinity to negative 3, and from where x equals 3 or is close to 3 to positive infinity. So those are the positive parts of our graph. If we want to highlight the negative parts of the graph, I'm just going to do that in green. The green part, or this segment, is going to be the negative part of the graph. So if we were to jot down the interval where this is negative, we say it starts when x is negative 3 and it ends when x is positive 3. So what we're really saying is between negative 3 and positive 3 for x values, the graph is sitting below the x-axis. So we're actually using those intercepts as sort of the dividing points. Now, what you'll notice is I've used round brackets everywhere because I can't include negative 3 or positive 3 in any of these cases, because if I put my pencil right on negative 3 or positive 3, I'm not completely above or below the x-axis, so I can't say that that qualifies as a positive or negative part of the graph. So be mindful of your brackets, but we'll be analyzing those different types of criteria when we look at graphs moving forward. Aside from that, we're going to be looking at maximum or minimum values. So when we talk about a maximum or a minimum value here, we're talking about the highs and lows. Now, maximum values are the high points on the graph and minimum values are the low points on the graph. So if we were to graph this parabola, for example, the vertex would be the low point or the minimum. And we'll get into some more examples when we start graphing with your calculator. But aside from finding all of those important pieces of information, we might be asking you to find specific x or y values. And again, we're going to show you how to use your calculator to do all of those things. So when you have a calculator exercise, you're going to be doing things like finding zeros of a function. You might be finding a maximum of a function, or you might be finding a minimum value for a function. I'll show you also how to use what's called the value function in your calculator, or to find a point of intersection. So we're going to take a look at examples that involve all of these different calculator functions. Our first example says, given the function f of x is equal to 2x squared minus 16 times x plus 20, find each of the following. So we're going to graph that function in your calculator and then start our points of analysis. But it's really important that you graph it correctly and that you find some critical values on that graph so we can analyze. Okay, so the function we want to graph is y equals, and I'm going to clear this old function out of here. So we've got y equals 2x squared, so 2x raised to the power of 2, and we've got minus 16 times x. So here's our minus 16x, and then we've got plus 20, so you're going to add 20 as your constant. So when we hit graph, I'm just going to make sure I'm in a standard window to start. When we hit graph, we almost see exactly what we need to see out of this graph, but we can't see the bottom part of the vertex here. So I'm going to change my window dimension a little bit and make my y minimum slightly lower. So maybe negative 15 will be sufficient. We can give that a try and see how that looks for your graph. So now when we graph this function, we see all kinds of good things. I see the x-intercepts. What I don't see is the y-intercept. So if you want to increase that y maximum, you can do that as well. So go back and change your y maximum. Instead of 10, maybe 20 will be sufficient. And then when we graph this time, oh, just about see everything. You might want to sneak a little bit higher. So y maximum of, let's say, 25 or 30. If you make these changes to your window dimension, then what I would recommend you do is make what I call a dummy sketch. So a sketch on your paper that has all of the important points that we're about to find. So in terms of graph analysis, what we need to find are the domain and range values, or intervals. We need to find the intercepts, where the graph is positive or negative, which again requires intercepts. We want a maximum or a minimum value, and then we want you to evaluate certain functions. So the first thing we're going to do here now is find our intercepts. So if we want to find the leftmost x-intercept, as you recall, it's second function and then calculate. Option 2 for a 0, so we want to find that intercept, and you can either move your cursor and sandwich to the left and right of that intercept, or you can type in values that are to the left and right. What we get here is approximately 1.6. I'm just going to round this to the nearest tenth. So on your paper, draw this sketch and label that intercept as approximately 1.6. Now we want to find the second intercept, so second calculate, option 2, and then we want to go to the left and right sides of that other x-intercept. So we've got the left boundary established, now the right boundary is established, and when we hit guess, you get roughly 6.4. So once again, we want you to make note that 6.4 is the approximate location of that second intercept. At this stage, we also want to find a y-intercept. So there are a couple of ways to do this. You can go second function calculate and choose option 1 for value. What this will do is allow you to type in your own x value, and it will tell you the y value at that point. So what we know about every y-intercept is that x equals 0. So you can type in 0 for x, and it'll retrieve 20 as your value for the y-intercept. Another way to see the y-intercept is just by using the table of values. So if we take a peek at that table of values, when x is 0, your y value is also 20. So both of those functions work well. The last thing we want to find on this graph is the location of your minimum point, or that low value vertex in this case, because it's a parabola. So if you go second function, calculate one more time, we want to find a minimum. So we're choosing option 3, or you can arrow down and choose option 3. And then we want to get to the left and right sides of that minimum point. And I give myself quite a wide margin here, just to make sure I have the actual minimum point within those boundaries. So we go to the left and right sides, and what you'll come up with is something close to 4. What I recommend, once again, is you label this point on your diagram or on your sketch so we can use those pieces of information moving forward. So we're back at our page, and again, I'm going to create that sketch that I mentioned when we were finding all of those good points on your calculator. So our sketch looked something like this. And we knew that we had intercepts at approximately 1.60 and approximately 6.40. So those were the coordinates of the intercepts for the x's and the y values. And obviously I haven't done this to scale, but that coordinate was 0, 20. The last piece of information we wanted to find was the low point on that vertex. So that coordinate, when we found it, was 4, -12. So now that we have all of those important points labeled, we can go ahead and answer all of the questions that follow. So if we wanted you to state both the domain and the range, the domain of this function, remember, goes from left to right. So we're saying how far left does that left tail reach? And even though it's pointing up to the sky, it sneaks over to the left forever. And we know if we go to the left forever, that's -infinity. So my domain is going to stretch from -infinity all the way to the right to +infinity. So we're looking along the x-axis to see how far left and right those tails are going to stretch. Range values, remember, are bottom to top. So we're saying, what are the y values included in this graph? How low does the graph go to how high does the graph go? So if I can imagine this is the low point on my graph, but we need to be mindful of the y value at that point because range is y. So my range will start at -12 for a low point, and I'm going to use a square bracket because I include -12 as my low point. So again, difference between round and square is round does not include that point, square includes that point, and I know I get as low as -12. Because range has to go from bottom to top or low to high, we know the tails of the graph sneak up towards the sky forever, so we can say the top end of our range is +infinity. Again, we never use square brackets for infinity because you can't include that number. Infinity is an increasing value, so it just keeps getting bigger and bigger. So we found your domain and range. Now in part B, we need to make note of those intercepts. So we did find x-intercepts at 2 coordinates, so 1.60 and 6.40, and you have to write them as proper coordinates. If we don't put 0 in that y position, then you're really not talking about an x-intercept, so be mindful of your notation. The y-intercept in this case we found to be 0, +20. So that sketch that we've drawn is really helpful when we need to go through and analyze things. The next part of the graph that we are interested in is the positive part of the graph. And by positive, we mean what parts of the graph are sticking above that axis. So if we highlight the positive parts of the graph, I'm talking about this branch here, and I'm talking about this branch over here. So if we need to describe positive parts of the graph, those are always written in terms of x values or from left to right. So the graph is positive from -infinity. Again, even though that tail sneaks up way high, it sneaks over to the left forever. So my graph is positive from negative infinity until I hit that x-intercept at roughly 1.6. I have to use a round bracket at 1.6 because it's not positive or negative at that point. It's sitting right on the x-axis. But I have a second interval that's positive as well. So that second interval starts at the far right intercept. So we say from 6.4 to positive infinity, which means the further right you go, again, you'll maintain a graph position that is above the x-axis. So we have two intervals that are part of our positive portion for this graph. Next, we want to determine which portions are negative. So once again, I'm highlighting in green the segment of our graph that happens to be negative. So the negative part of the graph falls between your two intercepts in this case. So the negative part of my graph is going to start at 1.6 and stop at 6.4. And again, I can't include it in either one of those. Now the next question we're asking you to find are either maximum or minimum values. So to start with, when we talk about a maximum, we're looking for a high point in the graph. Now, I can't put my finger on a high point for this graph, so for a maximum, we have to say there is none or it's not applicable. But there's definitely a minimum point we want to contend with. So the minimum point is the low point on the graph, so it's the vertex in this particular case. So we say the minimum here is at the coordinate for negative 12. So what you need to be careful of is that sometimes you have what are called absolute maximums or absolute minimums. Absolute means it's absolutely the highest or lowest point on the graph. So this minimum is absolute. If you see something called a local maximum or minimum, it's really just a peak or a valley. We also call that a turning point in some instances. We don't see that this minimum value has any lower portions of the graph attached to it. So the minimum that we found is in fact absolute.
Part E of this question asks you to evaluate f at 4, which is really function notation. So if you know that whatever's inside those brackets is your value for x, there are two ways for us to find or determine f at 4. You can go second function calculate, choose option 1 for a value, and type in the x value of 4, which is what we're after. That tells us that the y value when x is 4 is actually 12, or negative 12 rather. So that's one way we can find f at 4. And again, if you want to use your table, go second function and then hit your graph key, look at your table. Again, when x is 4, your y value is negative 12. So both methods are perfectly fine. You could do a substitution in the original equation if you'd like. You can substitute x equals 4 and get an overall value of negative 12. So there are multiple ways to find your answer. Now, before we go back to our slides, the next question says find the x value if f of x is equivalent to 60. Now, just a reminder that f of x is really y. So they're saying, what is the x value, or what are the x values when y is 60? The best way for us to do that is to actually map a target. So what I want to do is hit y equals, and I'm not going to change my original function, but I'm going to say y2 is going to equal 60, because I know if I let y2 equal 60, we're letting our y values equal 60 all the way along this graph. So if I hit graph right now, I'm not really going to see much of anything because I don't have a high enough boundary set for my y maximum. So if we go back to your window dimensions, go beyond 60. So maybe we choose a y maximum of 70 or 80. Once you hit graph, you see the parabola and you see that red line, which represents y equals 60. What we want to do is find the points of intersection between this red line or target of y equals 60 and the parabola that we've graphed originally. So I also want to change my window dimensions and see a little bit further to the right because I like to clearly see those points of intersection. So my x maximum, I'm just going to modify and make positive 15. So now that we see all of those points of intersection very clearly, it makes our task pretty easy. So as a quick reminder from earlier modules, second function calculate, we choose option 5 for point of intersection, and then we arrow closer to one of those points of intersection, the first desired point that we want to find. So in this case, I'm close enough here. There's my first curve, that's the parabola. Once you click enter, it jumps to the second curve, which is y equals 60, and then I allow it to guess. So we get a point of intersection at -2. So when x is -2, our y value is 60. Now, if we do that again, second calculate, option 5 for point of intersection, this time we want to go closer to the other intersection point. Click enter once you're closer to that second point of intersection. We know the second curve is y equals 60, so we hit enter a second time and we go ahead and let it guess. It tells us when x is 10, our y value is 60. So we've been able to use all of these calculator functions to analyze the curve as requested.
The last question is looking for x values when we have specific y values. So this is where on your calculator we graph that line y equals 60. So excuse the poor sketch here, but we graphed that line y equals 60 and we found points of intersection at -2, 60 and at positive 10, 60. So what they're asking for in part F are the x values if y happens to be 60. So in this case, we could say x equals -2, and we know that x is also equivalent to positive 10 because those two x values give us y values of 60. So what I hope you're recognizing is that the sketch you provide when you're finding all of those critical points on your grapher can be very helpful when it comes to actually analyzing a function from top to bottom.
So we now have a new function, y equals, we're in that y equals screen, negative x raised to the power of 3, or negative x cubed, minus 5x squared, so we've got minus 5x squared in here as well, plus 6 times x plus 1, so we've got plus 6x plus 1. Now when we hit graph in a standard window, I always like to start from standard position so that we can sort of see how the graph behaves without messing around with those window dimensions too much at this point. Now, what we want to see a little bit more of is the lower end of this graph, because this graph looks like kind of an S shape. So we want to see lower in your y values. So when you go to your window dimensions, we want to change that y minimum. I'm going to make it fairly extreme. Maybe I'm going to choose -50 for a minimum value, and we'll see what that does to our overall picture. Now I can see this is a smooth S-shaped curve, and we're going to learn more about this function type a little bit later in this module, but we now see all of the important points on your graph. So once again, make a sketch of what you see here so that we can clearly label all of the points we're about to find. So if we start with our x-intercepts, again, second calculate or trace, option 2 for a 0, and I'm going to go to the left and right boundaries by typing in -8, let's say, as my left boundary, and then I'm just going to arrow over to the right, or you can type in something like -5 for your right boundary. And when we hit guess, we get roughly -5.98, which would really round to -6. So I would consider that -6. So from here, we want to find the other intercepts. So second function calculate, again, a 0 of our function. So we want to sandwich that next x-intercept, which is a little trickier to do because it's close to the third intercept. So as long as I'm clearly to the left and right of that intercept in the middle of our function, then we'll find it clearly. So what we get this time is roughly negative 0.1. Again, make a mark on your sketch so that you know where that point exists. Then we have second function, calculate. We want to find that third intercept, that far right intercept for x. And once you sandwich it, we see that that third intercept happens at roughly 1.1. So make sure all three of those points are clearly labeled on your graph. Aside from that, we want to find your y-intercept. So I'm going to use second function calculate. Option 1 for a value. What we know is that every y-intercept has an x value of 0. So I'm just typing in 0, and we get a y value of positive 1 here. And the only other points I want to find before we get too much further are these low and high points of the graph. This is what we call a local minimum. It's not absolutely the minimum point on the graph because we see the tail of the graph sneaks further down. This is what we call instead a local minimum. So it's a little valley in the picture that we see. We also see a little peak, so that's considered a local maximum point. So again, we have local maximum or minimum points in this case, and we want to find those values before we move away from our graph. So second function calculate, we'll do the minimum first, and we want to sandwich that local minimum. So if we get to the left side and click enter, then we move past it to the right side and click enter, then we let our calculator take a guess, and we get roughly negative 3.9. So please make sure you make note of both x and y values for your maximum or minimum coordinates when you put them on your graph. Now to find that maximum, second calculate, we have option 4 for a maximum. And we want to move your cursor to sandwich that maximum point. So enter, move further to the right, we hit enter, we've sandwiched that maximum, and the guess we take is 0.5. So again, make note of that coordinate, 0.5 for an x value, and roughly 2.6 for your y value.
So you see now I've established the sketch and we can go ahead and label all of those critical points. So we have an intercept at negative 6, 0. We have a minimum point at negative 3.9 with a y value of negative 39.1. We have another x-intercept at the coordinate negative 1, negative 0.1. Let's fix that, 0.10. We have a y-intercept of 0, 1, so lots of confusing points with all these ones. We have a maximum here of 0.5 and 2.6, and we have another intercept, our third intercept, at the coordinate 1.10. So now that we've got all of these critical points mapped out, it makes the analysis part very easy. So remember, for domain and range, you have to be very mindful of whether you're talking about x values or y values. So domain is how far left to how far right the graph goes. The tails of the graph head in opposite directions, but they sneak further to the left and further to the right. So we can say that the domain is from negative infinity to positive infinity. And range are the y values that are included. So we're thinking low to high. One tail sneaks down towards the floor forever. The other tail sneaks up towards the sky. So the range is going to also be from negative to positive infinity. Now we can record your x-intercepts properly here with good notation. So we have negative 6, 0 as an intercept. We have negative 0.10 as our second intercept, and we have 1.10 as that third intercept. For the y-intercept in this case, we already found it to be 0, 1. And from here, we're ready to analyze positive and negative parts of the graph. So where this graph is positive, just as a quick reminder, is sitting above the x-axis. So if we start with the positive parts of the graph, I see that first branch is above the x-axis. Then we have this middle segment as well that is sitting above the x-axis. So if I wanted to describe that in interval notation, remember it's x's from left to right. So the graph is positive from negative infinity, which means as far left as you could imagine, until we hit that first x-intercept at -6. Again, round brackets because we're not allowed to include that. The second positive part of the graph, that little bump in the middle, starts at -0.1 and continues to +1.1. So those are the positive portions of our graph. If we change color here and we look for negative portions, I see actually two segments of this graph that are also negative. So we again want to describe them using interval notation for x's. So this graph is below the x-axis from -6, or that intercept, until it hits the next x-intercept at -0.1. So again, if you're tracing between -6 and -0.1 for your x values, you're going to be below the axis. Then we have another segment of this graph that starts at 1.1, or that far right intercept, and continues indefinitely. So continues to positive infinity, because if I trace further to the right, I'm going to remain below the x-axis. Now in part D, we want you to find the maximum or minimum values. So we have a local max, or a local high point, at that coordinate 0.5 and 2.6. Remember, there's a difference between local and absolute. Local means it's a little peak or valley. Absolute would mean that it's absolutely the highest or lowest point on the graph. We can see that the graph goes higher or lower than these sort of peaks and valleys. So these are in fact local maximums. Or we have a local minimum as well. And that local minimum we found to be at -3.9 for an x value and -39.1 as our y value. So we've been able to find all of those points of analysis based on those critical values that we found on your calculator originally. The next part of our analysis asks you to evaluate f at -3. Just a quick reminder, whatever's sitting inside those brackets is your replacement for x. Even though you could do a substitution into your original equation, you've got your calculator handy. So if you type in an x value of -3, what you'll get for a y value is -35. Or again, you can take a peek at your table of values and analyze that way as well. You'll see the coordinate -3, -35 listed on your table. Now the last question, once again, is giving us a specific target for y. So they're saying find x if f of x is actually -2. So just a reminder, that means y is -2. What you need to do is go into your calculator screen and graph that second function. So a second function, or a target of y equals -2, would look something like this. And I'll use a different color to draw this second line here. So your second line, y equals -2, when you graph it over top of your original function, would look like this. And we're looking for the points of intersection because every point of intersection between that red line and your original curve will have the specific y value that you're after. So when you find those points of intersection, what you will notice is that at x equals -5.9, which is this first point of intersection, you'll get a y value of -2. At x equals -0.4, you'll find a second point of intersection, this value, where again, y is going to be equivalent to -2, and then you'll find a third point of intersection at 1.3. So again, that's the third point on the far right where your y value is equivalent to -2. That brings us to the end of our homework section for 9.2. Please have a look at these practice questions and make sure that your calculator work is giving you the results that you need to have overall. So as always, if you have any questions whatsoever as you go through this homework, please make sure you reach out and let me know.